Welcome to this lecture series in linear algebra. In this lecture, we will discuss the notion of internal direct sum, and we'll also recall the notion of external direct sums, which we have visited earlier. Let us just discuss one definition before we proceed. This we have seen earlier. Suppose we have two subspaces of a vector space V. Then we define their sum in this fashion, and we have noticed that the sum is also a subspace. And let me just mention that all our vector spaces will be finite dimensional. Okay. So let us get into the notion of what is an internal direct sum. So suppose U and W are subspaces of a vector space V. Then we say that V is the internal direct sum of U and W if for all V in the vector space V, there exist unique U and W. So unique U in capital U and W in capital W such that little v equals U plus W. So every vector in the vector space V can be written as the sum of a vector in capital U and a vector in capital W, but in a unique way, right? So just to spell that out, if it so happens that U1 plus W1 equals U2 plus W2 for some U1 and U2 in capital U and W1 and W2 in capital W, we are forced to have this. So when every vector can be written as a sum of two things, one in capital U and the other in capital W, and in a unique way, then we say that V is the internal direct sum, or simply the direct sum of U and W. We don't every time mention this explicitly. More generally, suppose we have a bunch of subspaces, B subspaces of V, then V is said to be, then we say that V is the internal direct sum of these subspaces if for all vectors in V there exist unique vectors in the given subspaces such that V is U1 plus ... UM. Okay. Right. So that's the definition. And notationally, we just write V as U and then we put the symbol and a W. So when we write this, it means that U and W are subspaces of V and the fact that V is the direct sum of U and W. So this one single equation means all of this verbose thing. All right, and similarly here we write V as U1 plus ... UM. So this is another notation. Okay, so here is a criterion for deciding when V is the direct sum of two subspaces. So suppose you have two subspaces U and W of the vector space V, then V is the direct sum of U and W if and only if these two things happen. So the first is that you can write every vector as a sum of one vector in U and the other in W, and these two subspaces intersect trivially. Proof is very simple. So first assume that V is the internal direct sum of U and W. Then clearly one holds, because when we say that V is the direct sum of U and W, every vector in V can be written as a sum of a vector in U and a vector in W. Further, it can, this decomposition, so to say, is unique, but at the very least, you can write everything in here as a sum of one guy in here and one guy there. So this, of course, holds. And for the second, suppose little v is there in this intersection, then v plus 0 equals 0 plus v. Now think of this as a member of U and that as a member of W. We can think of this as a member of U because, well, this belongs to U. V belongs to both U and W, so we can think of it as a member of U. And on this side, just think of this as a member of U and that as a member of W. Now, since, as we mentioned, that this vector little v, this can be written in a unique way as a sum of a vector in U and a vector in W, we are forced to have that v is 0, and 0 is v if you want to write that. So v is 0 and 0 is v. So basically, we picked an arbitrary element in U intersection W and showed that it is actually the 0 vector. And therefore, this is the trivial subspace, meaning this subspace. So that implies both of these two things. And the reverse direction is also very easy. So assume 1 and 2. And let little v and capital V be arbitrary. We want to show that this can be written as a sum of two things, one in U and one in W, in a unique way. Clearly, you can at least find one such decomposition because one holds. So suppose V equals U1 plus W1 and also equals U2 plus W2. We want to show that U1 equals U2 and W1 equals W2. But this implies that U1 plus W1 minus U2 plus W2 is 0 because both of them are same, so their difference is 0. This implies U1 minus U2 plus W1 minus W2 is 0, which implies U1 minus U2 is W2 minus W1. But this guy is in W because it's a difference of two vectors in W. W is the subspace, so this is in W. Similarly, this is in U. And therefore, this is both in U and in W because, of course, this is in U and it is equal to something that is in W. So this is in both U and W. Well, all right, but by 2, U intersection W is the trivial subspace. Therefore, this is 0 and that is 0. And therefore, U1 equals U2 and W1 equals W2. So I'm not writing all of that, but it's clear. Okay, and as an open-ended exercise, find such a criterion for multiple. Suppose we have V equals U1 plus UM. So this happens if and only if some such conditions. So this is an open-ended exercise. I'll leave you to figure this out. Okay. So let's see some examples. So we have these two subspaces in R3. Let's say this is the origin. And sorry, so this is R3 and we have two subspaces. R3 is not the direct sum of these two subspaces because they do not intersect in the trivial subspace. They intersect in this line, which is a non-trivial subspace. It is a one-dimensional subspace of R3. All right, so that this is a non-example of an internal direct sum, while in this case, we have this subspace of R3 and that one-dimensional subspace of R3, and R3 is indeed the direct sum of these two things. And if you visualize everything here, everything in R3 can be written uniquely as a sum of one vector here and another vector there. So all one has to do is we have some, let's say, we fix this vector in R3. We come parallel to the line and meet the plane at some point. So we get this vector and we have sort of that vector. And the sum of these two vectors is that guy by parallelogram law. Here you can see that a given vector can be represented as a sum of a vector here and a vector there in multiple ways. So therefore, this is not a direct sum in that way also. Either you use the criterion or you use the definition. Both ways it's clear. All right. So now this is an important notion of a complement of subspace. So fix a subspace of a vector space V. Then we say that a subspace W of V is a complement of U if V is the internal direct sum of the two things. Right. So for example, if we have a subspace U, let's say this is my subspace U, then all of these subspaces are complements except the subspace U itself. Except for that one-dimensional subspace, every other one-dimensional subspace is a complement of U. So this example is R2. The whole vector space V is R2. This is U is this one-dimensional subspace, and it's easy to see that every other line is a complement. So by no means this complement is unique. Okay. So the lemma is that every subspace of a given vector space has a complement. All right. So here's the proof. So let U be a subspace of V. And all our vector spaces are finite dimensional. Okay. Fix a basis. Let U1 up to UM be a basis. of u. And we know that we can extend this basis to a basis of v. So let u1 up to um and w1 up to wk be a basis of v. So this is something that we discussed. Given a linearly independent list, you can always extend that to a basis. Okay, so just define w as the span of the wi's, and then it follows. I leave that as an exercise. It follows that the vector space V is the direct sum, internal direct sum of u and w. That's easy, so I leave it. Okay, so every subspace has a complement. That's nice. And now let us recall the notion of external direct sum and reconcile it, or maybe try to reconcile it with the notion of internal direct sum. So u and w be some vector spaces. They are now no longer any subspaces of a given vector space. It's just that they are two vector spaces over the same base field. Then we can define the external direct sum of u and w as, first of all, we have this set. We will define an addition, we will define a scaling, and this will be a vector space over the base field f. So that should appear in this quadruple, in this list, but I'm not doing it. So what is this addition function? Let me write this as v, because otherwise it will be very confusing. So this goes from v to v cross v to v, and here is how the sum is defined. So this is an element of v cross v. This goes to, under the addition, u1 plus u2, comma w1 plus w2. So this plus comes from the addition in u. The other plus comes from the addition in w, even though we use the same symbol for them. So that's how the addition is defined, and scaling function alpha comma u comma w. This maps to alpha u comma alpha w. And one can easily check that this is indeed a vector space. So given two vector spaces, one can create a bigger vector space. And here's an exercise. Dimension of u cross w is dimension u plus dimension w. So that's very easy. Once you have a basis of u and a basis of w, you can easily concoct a basis of this guy. And that will show you this. What else do I say? So the thing is, we don't use this notation. We don't write a cross product there. We still stick with u and this funny plus w. This is what we write, and one can get confused with the internal direct sum and whatnot, but with context, it is clear that, when u and w are subspaces of a given vector space, then when we want to think of the direct sum as a subspace of that parent vector space, then we just know that we are using the internal direct sum. If we don't, then we will be using the external direct sum, and generally from context it is clear. To reconcile the two notions, just note that there is a copy of u sitting in this vector space. So if we have a vector little u, we can associate with it this vector in the cross product. In this u cross w. And if we have a vector w in w, we can associate with it this vector. Right, and so that's how you can think of u sitting inside here and w sitting inside here. So u and w can be thought of as subspaces of these two, as subspaces of this bigger vector space. And this indeed is then, under this identification, the internal direct sum of u and w. In fact, if it is customary to just use the symbol u, and it is understood that we are talking about this guy. And in fact, you may see things like u plus w, and we may think of u plus w as a member of that guy. It anyway doesn't make sense on its own. U is a vector of one vector space, w is a vector of another vector space. There is no meaning of adding them as such. But when we write this, we actually mean the pair u comma w, which is an element of this external direct sum. So these kinds of abuses of notations are rampant, and I would encourage them. But if you feel that it is confusing in the beginning, there is nothing wrong with writing the full thing and sticking to ordered pairs and whatnot. Alright, so I think this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.